up on YouTube a few hours after class usually. It takes a couple hours for it to render, and it kind of depends on my schedule, but I'll usually get them up pretty quickly after class. All you need to know is what the link is to get there, and I'll show you that as we go through the overview. So, is anyone not familiar with D2L? That all pretty comfortable? So our course documentation is in D2L, syllabus and schedule, all that. The thing that's kind of a hassle with D2L is that you open one thing, and if you want to go somewhere else, you have to close the thing. That it's kind of very old school. The thing that's very nice about OneNote, all of our course stuff is going to be in OneNote. So in OneNote, this is going to be called the class notebook. So all of our whole semester is open right now, and that's what's cool about OneNote. It's open all the time once you're logged in. I am in the browser, not in the browser version, I'm in the app version. When you look in your student email and you get the email from SharePoint that invites you into our OneNote, when you click on that link, it's going to open it up in a browser. You don't want to use the browser version. When it opens in the browser, up in the top right, you're going to see a drop down, and you can click the drop down and you'll see Open in Desktop App. Once you open it in the Desktop App, then every time you open the app, it'll be there. Assuming you're using the same computer repeatedly. If you go to a new computer and open up the OneNote app, you won't see this class notebook because you haven't added it to that particular machine. So then you'd have to go back to the email and click to get it into the app version on that machine. So the benefits of OneNote, again, everything is open all the time. So if I come to handouts here are a bunch of handouts for the class. You just click through, there they all are. You don't open and close stuff. Everything is open all the time. Super slick, super easy to navigate around. Lots of benefits to using this setup. It's way more modern. We're breaking the class into 3 units. So chapters 6 and 7, this is going to be our first unit. Our first exam will be on chapters 6 and 7. All right, then we'll get through that. And then our second unit, chapters 8 and 9. Then we'll have an exam, exam 2. And then unit 3 is going to be chapters 10 and 11. Calc 2?
Yes.
Welcome. So that unit 10 and 11 is the one you've probably heard horror stories about, Infinite Series, Power Series, those types of things. That's sort of the gauntlet. It's kind of what a lot of people think of as the hardest part of all of calculus, is dealing with infinite series. And then we do a couple sections in chapter 12, and then we'll have our final exam. So the cool thing, again, is that everything's open all the time. So when we're in here looking at our chapter 6, here's chapter 6. Here are all the sections in chapter 6. I'll put all the notes on the board, record it all at the end of class. It's up there on YouTube. So it gives you a lot of opportunity to go back if there's something you don't understand or you want to revisit. You can go back, or if you're going to miss class for some reason, you can go watch it on YouTube, play it at double speed or whatever you need to. If there's something in particular that you're totally hung up on in class, just figure out where we're at, make a note of it in your notes, make sure you can find it quickly in the YouTube video, whatever works best for you. But again, so we can just zip through, and once all the notes are up there, they're up there and easily accessible. Another cool thing at the end of the semester, right now you're going to be opening this OneNote in your school account, but you can also have a personal OneNote account, like on your computer. You can have your school account. You can also have a personal account. At the end of the semester, you can export this notebook and you can have it forever. If you're going on and you want access to your math notes, instead of having a big 3-ring binder like I go out in my shed, and I've got these boxes of binders that I haven't opened since the early 90s, just sitting there. Now that everything's digital, you can just pop that notebook into your personal OneNote account, and you've got it, as long as you need it or want it. So that's kind of cool. So it's got a lot of benefits. So our course is going to be comprised of homework and quizzes, which will be done in MyLab Math also known as My Math Lab, depending on how old you are. So all the homework and quizzes are going to be in My Math Lab. Has anyone not ever used My Math Lab? I'm old, so I call it My Math Lab. I've used it since the first month it came out, 20-something years ago. So I tend to always call it My Math Lab, but it's the same thing. It's My Lab Math, My Math Lab, same thing. There'll be a link in our course, I'll get to it in a minute, that will take us into My Math Lab. You should go right in. You don't need an access code or anything. Access codes are built into your tuition these days. If you are retaking the course, you can get a refund on that access code, because if you took this course in this format, you've already paid the access code. And so if we go to D2L, you will see the, that is me, you will see an announcement that tells you what to do if you want to get a refund on that. And I'm sure I just fat fingered that. No, I didn't. So if you come to our course, you will see announcements, and one of them tells you how to get that current. It's a $80 or $85. It always goes up, of course, every year. I forget what it's at right now. But if you've taken this course in this format at this school before, then you can do this and send the bookstore an email with this information, and they will strike it from your account before they actually take it out of your account. So if you need that refund, or if you want that refund, do it. This in D2L, this is a link to our Spring 25 course lectures. So you can get to the link right there. If you're in OneNote, the link, if we come up here to welcome, so the top section up here, here's our schedule. This is probably the most important document in the course. We'll stick to this schedule. It's got all the important date information down here. It's got the grade breakdown down here. So quizzes 15%, exams 16% each, final exam 22%. Homework right there is 10%. And the worksheets will be 5%. What are the worksheets? So homework and quizzes in My Math Lab. Infinite attempts at homework, 2 attempts at each quiz. Best quiz counts. At the end of the semester, 3 homeworks are dropped. 1 quiz will be dropped. There's 7 quizzes. The quizzes are based on chapters. The homework is based on sections. So a ton of homeworks, 1 quiz for each chapter. The worksheets. So the worksheets are 5%. There's going to be 3 scores. Those are done in OneNote. Due dates are right here, February 6th, just Chapter 6, not Chapter 7. Second unit, just Chapter 8, not Chapter 9. And then down here, Chapter 10 worksheet, none on Chapter 11. So it's set up this way. The worksheets are supposed to be sort of basic skills types of things, not super in-depth problems, more very important skills that you need that you build on to do the more complicated and more abstract work. And so the way I have them set up is that they're due here. I'll mark just really cursory grading, yes or no. It's right or it's wrong. Anything that's wrong, turn it in on exam day, and then I'll grade it for points. Okay, so no points will come on the initial submission. Give you an opportunity to correct any mistakes you've made, and then I'll grade it after that. Does that make sense? So those are going to be very helpful in order to get the basic skills down, most important types of skills. But I need this little buffer here. I don't want to put Chapter 7 on there, then it gets too jammed for me to give it to you and get it back and grade it. So I'm just doing the first chapter in each of the units. So worksheet on Chapter 6, 8, and 10. Okay, and nothing on Chapter 12. So in this OneNote environment, there are a couple things. There is this collaborative space. This is space that you and I can both have read and write privileges. This is a great place for you to ask questions. If you have a question, you can click right here, and Did I put instructions at the top or not? Well, I guess I'm telling you the instructions. So if you click here, you can come in and change that name. If you're in chapter 6, section 5, question number 42 or whatever, you can just put it right there. Just change this so when I look at this, I see that something's been changed. So I know to look. And then you can put in your question. You can type. You can, in OneNote, if you have a tablet type thing, you can write. The really good thing about OneNote is it's very easy to add content. If you're on MyMathLab, you can take a screenshot and just paste it right in there. So lots of ways for you to add stuff in there that I can then respond to. Everybody know how to take a screenshot? In Windows, you've got the snipping tool that can grab any sort of piece of the screen you want and then just paste it. The drag about this collaborative space is that they don't have notifications. So if you put something in there, I don't get a ping that there's something that's changed. So I need to be proactively looking at it. If you put something in there that you have a question on and you'd like a prompt response, if I haven't replied in half an hour, go to email and just send me an email. I get email on my phone, I get the ding, and you say, oh, I've got a question that I posted in OneNote. Can you take a look? Then I can just jump into OneNote, whether it's on my phone. OneNote works fine on the phone, pretty easy. Then I can get in there and answer it. So if I don't respond promptly, like if it's some weird time of the day or the weekend, just send an email. And the best email to use is not the D2L email. I'm sure if you've used D2L, you kind of know that you can't just hit reply. If you have your D2L email forwarded to your Gmail or whatever email you use daily, you can't hit reply in that Gmail account to a D2L email. So it's kind of a pain in the butt. So it's better to email me at my school account, then I can just hit reply. So if you do the email through D2L, it's a closed system. So that's kind of a hassle. So email me there. I get those emails all the time. If you put something in OneNote, just say, please take a look at OneNote. I've got a question. Can you take a look? I'll get to it and look at it as quick as I can. So that's the collaborative space. Then we have the content library, which is where I have read privileges and you only have write privileges. That's where all our lecture notes are going to be in here. And then there's the private space for myself, the teacher-only section. So here's where our worksheets are. There's all stuff in there. And then each of you have your own space. You have read and write privileges to here. I have read and write privileges to here, but you can't see each other's work. It's private. Super cool. So you don't ever turn anything in. When you come to your worksheets here, there's the worksheet. As soon as you start doing your work on here, whether you write, whether you take a photo of paper pencil work and insert it, however you do it, it just shows up in here automatically. You don't have to hit submit. You don't have to hit anything. When the due date comes, I just hit this lock button, and then you can't write anymore in it. It's going to say read only at this point. So it's super easy. You don't have to turn anything in. If you take an exam in the testing center because of an accommodation or because of a makeup because you're sick or something, they send it to me digitally. I can now put it in here and return it to you through here. Like, it's super easy to send work back and forth. It's not even really sending. We're just collaborating in the same space. So here is the first worksheet. Lots of ways. Again, you can use, if you have a tablet type device, you can just write right in there. The one drag about writing in there is that you have this weird issue if you try to make more space. The ink is detached from the background. So that's kind of a drag. So in OneNote, if I wanted to add space, there's this insert space thing here, I can add space. But if you have ink in there, then the ink is going to be, it's not going to be attached to the background. So you can either increase or decrease space with that insert space thing. So you just have to be a little careful if you use ink. Most of the people that I have worked with tend to like to do it on paper and pencil or something else and then just do a quick screenshot of it and paste it in. If I come to another notebook here, let me go to, I don't have any others loaded in here that actually have examples of work, so I can't quite show you. But if you get comfortable with the photo, send it to your computer, and then just drop it in. That's a pretty easy way, and then you don't have to deal with the space thing. So whatever works for you. Try a few things. Ask me, is this working, is this not working? Try a method. Figure out a method that you can do it efficiently. You know? Let me know if you have questions as we're going through here. Just stop me if you have a question. So, any questions yet? Everyone know about the Math Center? Down in the library, L280. So if we come up here to the welcome again, most important document is our schedule here. Here is the link to our YouTube playlist. Click on there, it'll take you to our playlist for this semester. There's nothing there yet because today's day one. Here is the schedule for the Math Success Center. Our class is Calc 2. So if you want to be in the Math Center when somebody can actually help you with Calc 2, look under this column for the yeses, and then just match the names up here. So our class is Tuesday and Thursday. I am in the Math Center every Tuesday afternoon and every Wednesday morning, from 9 to 11 on Wednesday morning. Some of the folks that can help you with Calc 2, Steve Wolf teaches Calc 2, he can help you. Steve Yamakowski, he has taught Calc 2, he can help you. If you look at that list, try to figure out a time where you can go. This class is hard for a couple reasons. The content's hard. The format's also a little hard. We have 2 days a week. When I was in school, we had Calc 2 5 days a week. So if I was confused after 10 minutes in a 50-minute class, muscle through, go home and figure it out. If you get confused in the first 10 minutes of a 2-hour and 15-minute class, you got a long way to the end. And then you've got 2 hours of confusion. To try to go sort that out is not trivial. The best thing you can do to avoid that is to read ahead. It's really hard to sort of capture some of the Calc 2 and Calc 3 type of concepts on the fly cold. To actually feel like you could formulate a question the first time you see something is very hard. If you read ahead, and then you come into class and I'm sort of going through it, it's going to be much, much easier for you to both comprehend it, much easier for you to ask a question before you get in over your head type stuff. So as you get deeper into these classes, this is not an upper level class, but Calc 2 and Calc 3 and Physics 2, those 3 classes are like the hardest undergraduate classes like in any subject. So you really have to start changing your state of mind when you're in these courses that act like upper level courses. You really have to sort of be proactive, read ahead, so that you know what to expect. It's going to be a lot easier than just coming in cold and I start talking about infinite series or infinite sequences or whatever it may be. 2 hours and 15 minutes is just a long class to try to figure it out on the fly. So that's my recommendation. I've been teaching this class since before all of you were born, probably. So I'm speaking from experience. I didn't just read this on the internet. So my office is in the math area, B1317. It's on the syllabus here. So at the top of the syllabus. The syllabus these days is the most miserable document that you encounter in a class. The syllabus used to be very personalized to what really is going to happen in the class. Now it's this legal document that has a ton of mumbo jumbo in it. And should you look through it? Yes. Is it the most important document in the class? No way. So the schedule is the most important document. From the syllabus, the most important things are, when can you drop and get a refund? When can you drop and not have an F on your transcript? And how is the grade breakdown? those are the most important things. But obviously look through this and ask me if you have any questions on it. So my office, B1318, over in the math area, and my department chair is named Stephanie Beck. She's actually not on this campus except one day a week. We're in this transition of a very strange administrative redesign. So definitely look through this. The schedule is at the end of it. I mean, it's just a bunch of stuff that talks about transferability, and obviously this course transfers to all of the schools in the state instantly. It's guaranteed transfer. That would suck if it wasn't. Grade breakdown is there. So again, the most important thing are probably dates and things. Oh my gosh, the pain. There. Why do they put the dates here? Don't you expect, like when I open a syllabus, I expect the important dates to be right at the top, not on page, whatever page number we're at down here at the bottom. But I've taken the important dates and I've put them in the schedule here for you. So take a look at it. Let me know if you have questions. But don't get hung up on all the words in here because it's just this, it's alphabet soup.
You can get the syllabus on my courses, right?
So if you go into my courses, aka D2L, it's also there. So if you come, I just left our course. So if you come into our course and you go to content, you'll see the syllabus there also. So right there. So if you come into so in D2L, under content, that's where you're going to find all of our links. So here's how you get to my math lab. So you're going to come here, and you can enter my math lab in lots of different ways. You can enter through the assignments. You can enter through the grade book. My math lab keeps track of all your grades, of course. I will put our exam grades in my math lab also. In D2L, I am only going to put your quiz average, your homework average, and then your exams will be in there also, and your notebook average. I'll update that after each exam. So after each exam, I'll put your exam score in D2L, I'll put your exam score in my math lab, I'll take the averages in my math lab and pull them over to D2L. So D2L is just going to be kind of a summary of the important categories. My math lab will be the ongoing grade book, which is probably going to be more accurate because we only have 3 exams and then a final. So D2L's grade book's only going to be most accurate the week after the exam. So in my math lab, though, that's going to keep your running tally of your grade. Homework and quizzes, click right there. These 2 things are the most underutilized pieces of my math lab, which is sad because in the multimedia library, you have all the content that is available for this book. You can go in and there are hundreds of questions, hundreds of exercises, hundreds of videos, everything is in there. Homework and quizzes are just a subset. So if you're in Chapter 6, Section 5, and you're stuck on a topic, you can go to the multimedia library and you can do a bunch of extra questions. The homework that's assigned is very little. For most people, that's not going to be enough. The homework and quizzes that are assigned is the bare minimum. If that's all you do, the chances of getting an A is small. Like that's just the bare minimum. If you're not getting 100 on your homework, you are slacking. When you have an infinite number of attempts at every question, you should be hitting 100 on your homework. But that doesn't mean that you're going to understand every concept because the homework, it has all the help me solve this, view an example. It's very easy to game it and not get it. You can always go into the multimedia library, the topic that you're stuck on, look at a bunch of other problems and just do extra practice. So if you really want to do well and you really want to get the content because you have to take Calc 3, you can't do Calc 3 without a solid integration background, which is what Calc 2 mostly is, learning how to integrate well. That's a great resource for you. And the study plan is similar. You can go in and you can drill down into Chapter 6, Section 5, and you just see everything that's available for Chapter 6, Section 5. So these 2 things have a lot of extra resources, a lot of good videos. So you can get to those right there through my math lab. Then there's our course documentation. And then PDF notes. I don't know how everyone wants to take notes these days, but I've screenshotted all the sections one by one. Some people like to go to Kinko's or whatever and print them all out and put them in a 3-ring binder and write paper pencil. If that's your jam, you can do that. Others like to use digital stuff and write into OneNote. You can do that. Another cool thing about the OneNote class notebook, as I write on there, it instantly shows up on your computer. So if you have OneNote open and you have our class notebook open, as I write on the board, it shows up instantly on your machine. So that's kind of cool too. If you're at home and you're sick, you could actually open up your computer, open up OneNote, and as I'm writing, it's going to show up right there if you're home, sick. So that's kind of a neat feature that it's live. So whatever your note-taking strategy is, go for it. The one thing you don't want to do, the one thing that I had to do, was write every single thing down and every single thing that was said and not written on the board. It is impossible. When you get into Calc 2, Calc 3, it is impossible to write every single thing down, every single nuance that's mentioned, and be digesting any of it. It's way better to take more sparse notes and then look at the class notes afterwards. You're not going to be able to track some of the important concepts if you're literally scribing every second. There's just too much information. When I was in school, that's what we had to do because we didn't have resources on YouTube. We didn't have resources like this that are going to be posted to D2L or to OneNote or whatever. So you have to figure out the balance, and for everybody it's a little different. Most people need to be writing something or you start spacing out. But you really don't want to be writing everything because that's not going to be the best way for you to comprehend as we're going. So those are there. Some of the sections may not match exactly because I am always in the process of editing OneNote. If you come across a section and it looks a little bit different or there's some missing questions that we're doing on the board, just let me know and I can update it if that's what you want to do, is use the PDF type stuff. Okay, so that gets us started. Let me just reiterate that everybody has OneNote. It's part of Microsoft 365. All of you, as long as you were on the roster this morning, all of you have an email in your CCCS email, your student email, the .student.cccs email. If it's not right there in your inbox, click the search button and type SharePoint. Microsoft's inbox sometimes hides emails in weird places. If you just search for SharePoint, it will be there, if your name is on the roster. Click on the link. The link is going to open in a browser. You do not want to use the browser version of the app. It's very limited. In the top right corner of the browser, you're going to have a drop-down menu. Click that, and it will have an option that says Open in Desktop App. That's where you want to do it. And once you've done that once, on whatever computer you've done that in, every time you open up OneNote, you'll see all your notebooks over here. So in this classroom, because I haven't taught in this classroom in a long time, I only have the 2 notebooks here that I opened up today. So if I want to look at my notebook from last semester in my office, I've got a pile of 20 notebooks sitting on my desktop there. But here, if I wanted to open up a previous notebook, I would have to come up here and click File and click Open, and I would have to go find a prior notebook. Okay, so whatever computer you're on, it's not going to automatically be loaded on that computer until you click that link and click Open in Desktop App. But once you've done it, then it's always there. All right, any other questions that you can think of before we start doing what we're all here to do? Anyone think of a question? Obviously, as questions come up, just ask. Just ask.
If I want to do this on paper and then take a photo, is it easier to do JPEG and turn it in, or PDF?
PNG file is usually the best. And so if you take a photo, so there's a couple of ways. If you have OneNote on your mobile device, you can just drag that photo right over. And I think when you do that through OneNote, if you use the There is a capture tool built into OneNote. I forget exactly where it's at. If you use that capture tool, I believe it will automatically put it in as a PNG. If you upload it to your desktop computer and then you're just going to drag and drop it over, I believe if you just drag and drop it, it turns it into a PNG, I believe. And if you use the screen capture, the window snipping tool, then it always does it as a PNG. PNG is easiest because it's small and it's pretty accurate. Yeah. And you can do JPEGs also if you have it as a JPEG, and we can see if it doesn't come. Because you're only going to be doing it intermittently, it's not a big deal. My online class, if you did JPEGs, would create these huge files, which then make things really complicated. But for this class, it might work fine. We can test. We're figuring it out as we go. This thing is going, right? That thing is going. If I start class and I don't hit the record button, just remind me. Oh, I didn't take roll yet. I need to figure out who the heck you all are. It's going to take me a couple weeks to put names to faces. So maybe I'm going to wait and take roll at the more around the break time, so we don't be more efficient that way. Do it right around then. So class starts at 9:30. Usually we're going to take a 10-minute break at 10:30. So maybe I'll just mill around during the break and you take roll that way. Might be easier. Okay, so let's go ahead and get started with the math. The first topic, we are going to be looking at some things that most of you have probably already have some experience with. Things like position, velocity, and acceleration. Maybe not all of you have had physics, but at least these concepts should be semi-familiar. We're going to talk about a very limited case where we imagine motion on a line. So we're not throwing a ball. We're in the most boring case imaginable. There's just like a point or a particle or a ball just moving back and forth on a line. Dizzy, very, very boring. Dizzyingly, just so boring. But it's where we start. So we don't call it, some places might call it linear motion, but that sort of implies something about the nature of the function that's defining the motion. It doesn't have to be a function whose velocity is linear. So usually we try to say motion along a line. You can have motion along a line where the motion is exponential. So I don't like calling it linear velocity. We'll call it velocity on a line, or motion on a line. So the idea is that t is going to stand for time, and we are going to imagine this number line. And of course, 99% of the time, it makes the most sense to call the positive direction to the right and the negative direction to the left. If you wanted to reverse it for whatever reason, you could. But in this class, motion on a line, positives to the right, negatives to the left. When you get into physics, of course, sometimes you'll do vertical. Positive is up and negative is down. But for us, positives to the right, negatives to the left. And we are going to look at the position at time A and time B. And what we're imagining is the location on this number line. If we plugged in t equals a, s of a is just the number on the number line where the particle is at time A. Similarly, at time B, s of b is the number on the number line where it is at time B. S of b minus s of a, that's going to be the displacement. That's going to be the change in position. And it is a net change, meaning that it can be positive or it could be negative. So if we end to the right of where we started, and positive is to the right, we have a positive displacement. If we start on the right and end up more to the left, we're going to have a negative displacement. So displacement, positive or negative, terminal position minus initial position. Why we use S for position, I forget. Some Latin word that I've long since forgotten. So one of the applications that we know is that the derivative of position is going to give us velocity. Everyone familiar with that? Derivative of position is velocity, rate of change. Derivative of velocity is acceleration. So we have that little back and forth sequence. You can go from position to velocity to acceleration by differentiating. And you go the other way from acceleration to velocity to position by integrating. Right? So back and forth, derivative one direction, integration the other direction. So at this moment, we're thinking, okay, well, we've got this S of B minus S of A. That means displacement. We already have a mathematical way to find that displacement. That displacement is found by doing one of the most important things that you learned in Calc 1, and that is the definite integral. And we know that the velocity is the rate of change of position, S prime. And we know from the fundamental theorem of calculus part 2, if you integrate a function, if you know an antiderivative, boom, right there, you plug in the upper endpoint, you plug in the lower endpoint, and you get this S of B minus S of A. So S of B minus S of A, we have a mathematical way to find that. We integrate the derivative. If we integrate the derivative, we will get S of B minus S of A. So this right there is our formula for displacement. If you integrate the velocity function, you will get the displacement along the interval. Great. We do not have a name for all derivatives. So S prime we know is V, but in general, we might not have a word that describes that relationship. So sometimes this will just be another function right here. All right, let's go to the next page and let's try to refresh ourselves on some basic integration concepts. So we are talking about functions of x. So we're imagining our function of x. Function of x means, it has to pass the vertical line test, can't pass under itself like a circle. So we've got our function here. We are thinking of the x-axis as containing the domain. And so if we look over here on the left, we have a region between the curve and the x-axis that's above the x-axis. Here we have a region that's below the x-axis. And if we think about area, both of these are positive area, right? Those areas are positive. But if you were to integrate from A to B, what's built into the integral is upper area minus lower area. So it's got that signed nature built right in. If you were to integrate from A to B, the answer is going to be A1 minus A2. That will be the answer. If you were to just integrate from this point, let's say C, to B, you would get a negative number. And the negative number that you get will be minus 1 times whatever that area is. So if you integrate a curve that's above the x-axis, you're getting the area below it. If you integrate a curve that's below the x-axis, you get the area between it and the x-axis times minus 1. So if you integrate a curve below the x-axis, you are getting a negative number. Okay? And so the nice thing about the definite integral is that you just integrate A to B, it automatically does the upper minus the lower for you. It does S of B minus S of A. If we go back to our line thing and our particle is bouncing around back and forth on the line, if we want distance traveled, that is very different than displacement. When you drive from home to the college and then back to home, your displacement is 0. Your distance traveled is clearly not 0, right? So we need a method to figure out what the distance traveled is. Sometimes that's more important than displacement. So what we do in order to find distance traveled, instead of integrating just the velocity, what we integrate is the absolute value of the velocity. The absolute value of the velocity is called speed. If you integrate speed, you get the total distance traveled. Okay, so here is a picture of absolute V. V is positive, then 0, and then negative. Now, if we take the absolute value of that, we get this. And if we integrate the absolute value function here, the net effect will be A1 plus A2 here, where this A2 is positive now. So that will be the distance traveled, will be the sum of those two areas. That'll be distance traveled. Now, remember, there is a lot of hidden information behind an absolute value. It's very easy to just sort of think, oh, we just make it positive. Just make it positive. Well, you can't just integrate an absolute value function. An absolute value function is a piecewise defined function. An absolute value function, there's no antiderivative technique that you learn that allows you to integrate it. When you're dealing with an absolute value function, do this. Right? There is no special technique. What you have to do is go back to the definition of what an absolute value function is. The absolute value of v of t is either v of t or negative v of t, depending on whether what's inside is positive or negative. So we just erase the absolute value bars if v of t is greater than or equal to 0. But if v of t happens to be less than 0, then we multiply by -1. That's how you make it positive. You multiply it by -1 if it's negative. So integrating a piecewise defined function is done in pieces. You integrate the top piece, you integrate the bottom piece. So if we come up here, oh, this is above the x-axis, so the integral of it, we don't have to do anything. The integral of it is just the integral of v. Here, oh, it's down below the x-axis, it's negative, so this area is going to be -1 times the integral from c to b. Or you could multiply it by -1 first and then integrate it. Regardless, you have to multiply by a -1 in order to get the area and not have that negative be part of the answer. So let's first conceptually go through a couple of these. So we've got this velocity function here. Again, we're on a line. Even though this picture of velocity related to time is in 2 dimensions, the motion is in 1 dimension. Ball bouncing back and forth. So that's what we're dealing with. We're dealing with some units here: time, seconds, distance, meters. Okay, so part A says, on what intervals is the object moving in the negative direction? So intervals where the object, the ball, whatever you're envisioning, is moving in the negative direction. So for us, that means moving left. What is the first interval where it's moving left?
0 to 2.
0 to 2. Parentheses or brackets?
Bracket.
How fast is the object moving at t equals 2?
0.
0. So it's not moving left or right at 2 because its velocity is 0. So we actually want to use parentheses because a bracket includes the point. We don't want to include the point because actually right at t equals 0, 2, 4, 6, the velocity is 0, so it's not moving left or right. So we want to use open parentheses here. So our intervals where it's moving to the left are where the graph is below the x-axis, so we're going to go 0 to 2, and then the second interval is 4 to 6. sense? So the object is moving to the left in those two intervals. And then, what is the displacement of the object on the interval 2 to 6? So let's focus on 2 to 6. What did we end up with? Did someone say the answer? So displacement from 2 to 6 would be 4. So displacement, the effective displacement is, if we're looking at a graph of velocity, it's going to be the upper area minus the lower area. It's going to be the integral from 2 to 6. So that displacement is the integral from 2 to 6 of the velocity. And the effect of that, the result of that is going to be whatever's above, the area above, minus the area below. So we are going to get 4. And they did give us units here. So what would these units be?
Meters.
Meters, exactly. So that would be our displacement on this time interval. So now let's jump to C. What is the total distance traveled from 0 to 6? So distance traveled 0 to 6 is the integral of the absolute value of V. So if we're going all the way across, so from there all the way across, 0 to 6. Not all the way across. 0 to 6, so let's go from there to there. What is the distance traveled?
44 meters.
So distance traveled is going to be upper area plus these lower areas. Everyone agree with that? So we're going to have 20 plus 14 plus 10, so 44. And again, units are meters. Part D, what is the displacement from 0 to 8? So displacement from 0 to 8, that is just the integral of velocity. And the effect of integrating, just straight up integrating, definite integral, is upper minus lower. So what are we going to end up with?
Negative 10.
-10. And this, again, is a measure of meters. I almost said distance. It's not distance, it's displacement, but the units for distance and displacement are both the same, meters. Describe the position relative to its initial position after 8 seconds. So, this picture here tells us the velocity at each time value between 0 and 8. Does it tell us the position at time 0? Do we know where this object is at time 0? Yes or no?
No.
No. All we have here is a picture of what its velocity is at time 0 and all the way up to time 8. But we do not know the location on our number line at time 0. So all we can say is what? Describe the position of the object relative to its initial position after 8 seconds. So where will it be 8 seconds after we start?
10 meters to the left.
10 meters to the left. That's all we can say. 10 meters to the left. If the initial position was 0, we could say, oh, the new position is at -10 on that number line. If the initial position was 20, we could say, oh, the final position is 10. But because we don't know where the initial position is, all we can say is 10 left of initial position. Any issues with the sort of global ideas with these concepts? So this kind of summarizes what we've been talking about. So S is the position function. It's giving us the position of our object at time t. The velocity of that object is nothing more than the rate at which the position is changing, the rate of change of position, so s prime. We know back from Calc 1 that the definite integral of v, what we need to do is find an antiderivative for v. Right here. We know that. The antiderivative of v is s, because s derivative is v. Because those two concepts go back and forth. If the derivative of s is v, that means an antiderivative for v is s. And then we also talked about distance in contrast to displacement. We have to integrate the absolute value function, which is easier said than done. If I give you a complicated absolute value function, you would have to break it apart into two pieces, and you would have to integrate each of those functions on those subintervals. Well, in Calc 1, this right here, this result is called the fundamental theorem of calculus. Usually they call it part 2. Usually the fundamental theorem is broken into two pieces, and the second part is when these integration limits are numbers, not functions, not variables, just numbers. That is usually called the fundamental theorem of calculus part 2. This down here, we need to talk about for a minute. This is the first fundamental theorem of calculus, or the fundamental theorem of calculus part 1. What do you notice about this limit of integration? Is that a number? No. So in math, calculus, a and b represent numbers. T, x, y, variables. Now, even though a is a letter and t is a letter, those letters have different implications. A, b, we think of the a, b, c, d. Those 99% of the time you're thinking of those as constant values. Things like t, x, and y, and often z, we're imagining those as variables. And so this right here is very different. This, when you have numerical limits of integration, this is going to give us a number. And that's going to be a number, a numerical value. That t disappears. We call this t a dummy variable. It is not really a variable. It's a dummy variable. It's just there momentarily to allow you to do the integration, and then you substitute in for that variable, and then the variable's gone, and you just have a number. So we call that variable, if the numbers in the integration limits are numbers, we call the variable a dummy variable because it's not sticking around. It's only there temporarily as you do the integration process. Very different than this. Down here, when you do this integration and you plug in those limits of integration, you end up with a function of what independent variable? This will be a function of what? What do you think the independent variable is? T. X is still a dummy variable. It's going to be gone in the end. The integration variable is always dummy. That's always going to disappear. So for example, if we integrate from 0 to t, something like x cubed, we do the integration. So we use that rule they called the power rule. Add 1 to the exponent, divide by the new exponent anytime you have a polynomial. And then we plug in our upper limit of integration. We plug in our lower limit of integration. And I didn't do that very well, did I? If I plug in t for x, we get that. So this is our result. That result is a function. Everyone agree? Do we agree that that's a function? All right, so if you have a variable in your limit of integration, this is not a constant. This whole thing is a function of whatever that letter is, function of t in this case. So this is a function of t. So that is the second fundamental theorem of calculus. Now, S of 0 is our initial position. So if we are trying to forecast where this object is at time t, we first need to know, well, where is it starting? What's its position at time 0? Then we can figure out the change in the position over the interval. The change here is going to be a function, though. So if we add the displacement, which in this case is variable displacement, depends on what t is. But if we add that to the initial position, then we will figure out where we are at time t. So the position at time t will be where we start plus the change in position on this interval. And the next slide kind of lets us practice this. We'll do one example and then we'll take our break. So we're given a velocity function and we're given some units here. So we've got meters per second velocity. Determine when the motion is in the positive direction, when it's in the negative direction, find the displacement and find the distance. Okay, so there's our function. One thing that is super useful almost always when we're dealing with functions is a graph. The graph gives us a visual of what's happening. It really gives us an anchor into most problems. So let's go ahead and graph this just because it's going to help. You have to be able to graph basic functions. And what I'm going to do here is factor that quadratic. I see it's a quadratic, so I know the graph is a parabola. The leading coefficient, i.e. the coefficient of the highest power t, is positive, so we know it opens up. If we factor it, we can find the zeros really easily. So if we set this equal to 0, what are the two t values that will make that equation true?
2 and 0.
Does everyone agree? So if we can factor that into linear factors, then we set each linear factor equal to 0 to get the zeros for the function. It's a parabola. We don't really care about the graphing it precisely, but what we do care about is sort of the relative shape of things. And what we see right away is that t equals 0 and t equals 2, that parabola is going to pass through the t-axis at those places. So where does the vertex have to be at what t value? 1. Right? It's a parabola. It's symmetric around its axis of symmetry. If we know 2 zeros, and we don't care exactly what the v value is there, we're just trying to get a shape in our mind. And so we know that, oh, okay, this parabola, it's got to come down there, and then it's going to eventually, it's a parabola, so it's got to go out as wide as you can imagine. And if our time interval is 0 to 3, we know that it's positive over there somewhere. Again, we don't have to get super precise, just having a decent sense of what the shape looks like is enough. So what this tells us, and by decent sense, I now know that we're dealing with negative velocity right there, and I now know that we're dealing with positive velocity in there. Okay, and so now we can answer the first question. The first question said, where is it moving left and right? So where is it moving left? What interval?
0 to 2.
0 to 2. And again, we'll use parentheses, because at 0 and at 2, the thing's not moving. It's stopped. And it's moving to the right on the other interval. Now here we have a little room for conversation. At t equals 3, do you think we should include or exclude?
Exclude.
So we would exclude if the velocity is 0, but 3 is in the domain, so at that moment of 3, has the object stopped moving? No, it's still moving to the right, even though we're chopping off the domain there. So we actually will include here because the velocity is not 0 there, the velocity is positive. So at that moment in time, it is moving to the right. And then the next thing said find the displacement. So that's part B. So the displacement, that is the integral on the time interval. So we're integrating from 0 to 3. And we've got a function. It's not a piecewise defined function, so that's great. Our life is always easier when we don't have piecewise defined functions. Piecewise defined functions are always more complicated. So we'll integrate that function. It's a polynomial. It's our favorite type of function to integrate. Add 1 to the exponent and divide by the new exponent. So we add 1 to the 2, get a 3, divide by the 3's cancel. Similarly for the next term, add 1 to 1, get 2, divide by 2, 6 divided by 2 is 3. So then we're going to plug in our limits of integration. If you plug in 0, you get 0. If you plug in 3, we're going to get 3 cubed, which is 27, minus 3 squared is 9 times, 27 minus 27. So 0. So that's our displacement. So that's us waking up at home, driving to school, and going back to home at the end of the day. 0 displacement. No displacement. What does that tell me about the yellow area and the green area? They must be the same, right? This integral here does upper minus lower, so this is going to do the green minus the yellow, and if we get 0, that means those areas are equal in value. So that gives us a kind of clever way to find part C, the distance traveled. So distance is going to be the integral from 0 to 3 of the absolute value of v. Well, we can be clever and say, oh, let's just integrate, because we know this, because we know that, let's just integrate from 2 to 3 and double it. Right? Because the yellow area and the green area are the same. So if we go from 2 to 3 and double, or we could go 0 to 2, multiply by -1 to make it positive, and then double it. We could do that also. So there's a bunch of ways we could do it. So let's just do it this way, because this seems like the cleanest if we go from 2 to 3 of that function. Right? This function is above the t-axis here. So if it's above the t-axis, then its absolute value is just itself. Oh, I don't want those equal signs. Let's see. Try again. Can I get just this guy? There. That makes sense? So if we do that integration, we see that we are going to have the integral of the same function that we had over here, right? So that's going to still be our antiderivative. So we're going to have 2 multiplied by parentheses t cubed minus 3t squared, except our limits of integration are 2 and 3. So we'll have that. So 2 times, we plug in the 3, we get 0. And then we subtract off what we get when the lower limit is plugged into that antiderivative. 2 plugged into here is going to be 8 minus 12. 8 minus 12 is -4, so we're subtracting off -4. So we will get positive 8 as our answer. And these are going to be meters. Everybody follow? All right, let's go ahead and take a break. If you have any questions on any of what we've done so far. another velocity function. This one is exponential. And when you think about exponential functions, I hope you have a visual in your mind that looks like a ski jump or something, right? Big ski slope. Exponential growth is going to look like that. Exponential decay would be other direction, be going down. Exponential growth is going up. So this is going to be an exponential decay function because that exponent is negative. So it's going to be dipping to the right. Always good to get a sketch. So, and again, we don't need to be super precise. We really are just trying to get the relative connection between t and v. We're not being asked for anything super precise. What we know about exponential functions, though, is if we plug in 0, what do we get?
1.
So if we plug in 0 for this t value, e to the 0 is 1, and then 1 multiplied by 50 is going to stick us up here, up on the v-axis, up at 50. So we're up there somewhere. And again, this is exponential decay, so it's going to dip to the right. And we don't have to be very precise. All we're going to do is that. We know that it's going to dip down to the t-axis but never touch it. The t-axis is going to be an asymptote. And now we're only going 0 to 4, so this is going to be chopped off at some point. 0, 1, 2, 3, 4. So we're only going to look at part of this. So we're only going over to there. So that's what we're looking at. In this particular case, what can we say about the displacement and the distance traveled? Is there something that we can say about how those two are related? They're going to be the same, and the displacement will be positive. So they're going to be the same, right? Because this velocity function never goes below the t-axis. So that means that our displacement is positive. It means that our distance traveled is going to match. So in part A said something about the motion positive direction and negative direction. It's always in the positive direction. So it's going to be in the positive direction. So from 0 to 4, now we have that slight nuance. The velocity is never 0 here. At 0, the velocity is positive, so it is moving to the right when the velocity is 0, when the t value is 0. Similarly, at 4, it's still moving at 4 to the right. So it's moving to the right on 0 to 4. Displacement. So displacement, that's going to be the integral from 0 to 4 of the velocity function. Okay, so that means integral 0 to 4 of an exponential. Okay. One thing I know about multiplicative constants is that they are very mobile. That multiplicative constant of 50 can come out to the front. So we're sitting there. In Calc 1, you learned a technique the end of the semester for integration called what? There was a technique.
It's a U substitution.
U substitution. So if that was just a t, things would be wicked easy, right? If you were integrating e to the t, what would you get?
E to the t.
E to the t. It is the function that is its own integral and its own derivative. Very powerful function. When you get into differential equations, well, we'll do a tiny bit of differential equations, but in differential equations, that relationship is super essential, that the function is equal to its own rate of change. Okay, so if that was just a t, piece of cake, this is not just a t, which tells us we are going to use substitution. And substitution just changes the variable. So we're going to change the variable. We're going to say, hey, let's let u equal negative 2t. So in other words, we want to get rid of all the t's and turn them into u's. So you should have done this thing where you take the derivative of both sides down here, and you write it like that. Now, when you write it like that, there's kind of an intermediate step that's missing, which we don't ever write, but technically in Calc 1, you're saying, oh, the derivative of u with respect to t is negative 2. Right? If you were to differentiate this function, you're thinking of u as a function that's equal to negative 2t du dt, in other words, u prime, is negative 2, because that's linear. But then we multiply both sides by the dt, and this gives us this equation with differentials, a differential equation. And that's how we are going to relate dt with du. So this allows us to come up here and say, okay, well, we changed the exponent to u, so now it's just e to the u, which puts us in this category, right, where the exponent is just a single independent variable. So e to the u. Now dt, we have to replace the dt. We come down here, and you probably don't need to, but let's just be really thorough on this first example. If we isolate dt, we see that dt is equal to du over negative 2. So du over negative 2, dividing by negative 2, that can float to the front. That's just a multiplicative constant. Constants that are multiplicative can always just factor out to the front. So we'll just pull the negative 2 out to the front. Now the limits of integration. These limits of integration right here are t limits of integration. Right, that says t goes from 0 to t equals 4. T equals 0 to t equals 4. So we change those. So we come right here and we say, oh, that equation relates t and u. Tells us how to get to u from t. So if we are given a t value of 0, we can plug it right in there and see what the corresponding u value is. And I think it's pretty obvious that that corresponding u value is 0 also. So that t value gets plugged in right there, giving this u value. That t value gets plugged in right there, giving negative 8. So that's going to put a negative 8 as this upper limit of integration. All right. Well, we get negative 50, excuse me, negative 25. 50 divided by 2 is 25. And now what's the integral of e to the u?
0 to 8.
So we're going to integrate e to the u and get itself, and we're going to go 0 to negative 8. So 0 to negative 8. So this is going to give us negative 25 multiplied by e to the negative 8 minus e to the 0. And what is e to the 0? 1. So there we have it. And if we wanted, a lot of books hate having leading minuses. So a lot of books would distribute that minus and write their final answer this way. They're equal. I wouldn't care. So that is part B. We're measuring displacement at this stage or distance traveled. They're the same, so it doesn't really matter. So the units here are going to be meters. So that's supposed to be an M jammed in there. Put a little M in there. Make sure it's meters. Change the color maybe just so that number of meters. So this is going to be both distance and displacement. And I think, was it part C that asked for, yeah, distance. So this is part B and part C. So C is equal to B. Any questions on that? Okay. we are going to do a little integration practice here where I want to show you a technique that's called RCR. It's called reverse, I call it, reverse chain rule. So RCR, reverse chain rule. You all know what chain rule is, right? Chain rule, if you have y equals sine of 3x, you use the chain rule to write this as y prime equals 3 cosine 3x. Right, that's chain rule. You multiply, you take the derivative of the outer function, derivative of sine is cosine, and then you multiply it by the derivative of the inner function. The inner function is 3x, its derivative is 3. So that multiplicative 3 comes from the derivative of the inside. Similarly, if we had y equals e to the 4x, the chain rule would say that y prime is equal to
e to the power 4x, or no, 4 times e to the power 4x.
e to the 4x itself times the derivative of the exponent, so 4e to the 4x. Okay, so that's chain rule. So chain rule, you multiply by the derivative of the inside. The inside is the exponent for an exponential. It's the angle for a trig function. It's what's inside the square root if you have a square root function, the radicand. Now let me show you reverse chain rule. Notice right here. What is the derivative of this exponent?
Negative 2.
If we were doing chain rule, we would have multiplied by the negative 2. Where did the negative 2 end up? Did we multiply by negative 2? We divided by it. That is reverse chain rule. When you're differentiating, you multiply by the inside derivative. When you are integrating, you divide by it. So for example, if we have y equals, say, sine of 3x, and we're integrating the, let me write it as an integral. Let me write that differently. So if we are integrating sine of 3x, then the antiderivative, first we look at the outside function sine. What is the antiderivative for sine?
Negative cosine.
Negative cosine. So we're going to get negative cosine of the same angle. And then we go to the inside. The derivative of the angle is 3. If we were differentiating, we would multiply by 3. But because we're integrating, we divide by 3. And then you have to add a constant of integration. Okay, so what about if we were integrating e to the 4x? So if we are integrating e to the 4x, okay, the outer function is the exponential, the inner function is the angle, or not angle, exponent in this case. So the integral of an exponential is itself, just like the derivative of an exponential is itself. If we were doing chain rule, if we're differentiating, we'd multiply by that 4, but we are integrating, so we divide by 4. And then add a constant of integration. So RCR, reverse chain rule, works whenever you could do substitution where the substitution is a linear function. So this function right here is a linear function. This is a linear function, right? The power of t is 1. So whenever you have a linear function, there's no need to put in these 3 extra steps. Every single time you have a linear function and you're integrating, all you do is divide by the derivative of whatever the substitution is. So that is how we are going to do it in here. You can always do it with substitution if you want, But reverse chain rule is way faster. That is going to be the efficient way to integrate.
That only works when you're doing the use substitution, right?
Yes.
If the use substitution has a linear equation, then that's where we can actually do
Mhm.
it.
Yeah, we'll see a million examples this semester, maybe more. Okay, so here we go. Here we have another velocity function, sine function. Determine blah, 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 the same things, right? So determine the position function. Oh, this is slightly different. So using two different techniques, antiderivative technique and FTC technique, fundamental theorem of calculus. Okay, so I'm going to show you two ways to get to S from V. Two ways. The way that we've already done it once is the FTC way, where S is the initial position plus the change in position. And the change in position is found by integrating the velocity. So let's go through this. Let's first do it the antiderivative method way. Actually, I want to do this FTC method first because this is the way I prefer. So let's do it that way first. This way is more scalable and it's a little bit more conceptual. It illustrates some concepts that are super important. So let's do it that way. So our position function, the future position, is going to be whatever the initial position is, where we start. Again, imagine the line. Okay, figure out where we're starting. And then we're going to add this change in position on the interval from 0 to t. So if we're starting at 0, and we imagine t as a time value in the future, we want to know, well, how does the position change on that time interval from 0 to t? So we integrate from 0 to t, and we're going to integrate the velocity function. The one rub with this technique is that we have to be cautious with the dummy variable. We see a limit of integration of t right there. T is used now. T is going to be the independent variable for the antiderivative. So we don't want to use t as the dummy variable also. So we do want to integrate this sine function, but we're going to make a slight modification. Right? We know that the dummy variable is just going to disappear. So we can use whatever your favorite letter is. Right? That x isn't going to stick around. It's going to disappear and turn into a t because t is in the limit of integration. But you don't want to use the same letter to represent two different things. The dummy variable and the independent variable need to be different. So the one thing we have to remember is that, oh, already used t, dummy variable doesn't matter, favorite letter. In math, favorite letter seems to be x. So we're going to use an x when we integrate that sine function. So then we carry on our merry way. The position at time 0 is 1 plus integral of sine. Antiderivative for sine is negative cosine. So negative cosine of x on the interval 0 to t. This function right here is our antiderivative function. That's what we're plugging the t and the 0 into. The 1 is separate. Right? The 1 is out in front from s of 0. It's not part of the antiderivative. It doesn't get substituted into somehow. So we have 1. Now we could factor out that minus sign if we wanted, but let's not do it. Let's just leave it. So 1 plus. So now we have to do upper limit minus the lower limit. So we'll have that. Upper limit minus lower limit. And then the simplification of this, what is cosine of 0?
1.
Cosine of 0, so imagine your unit circle. Cosine is the first coordinate. Sine is the second coordinate. Alphabetical order, C, comma, S. Cosine, comma, sine. So cosine of 0 is 0 radians, 0 degrees. We're over there. Cosine is the x-coordinate, so it's going to be 1. So this is going to end up being 2 minus cosine of t. So there is our future position, aka our position at time t. So that is the better method. That is the FTC method. Here is how, if you were in Calc 1, how you would do it. You would do something like this. You would say S of t is equal to the integral of sine of t dt. You would use an indefinite integral. You wouldn't have limits of integration, and you'd break it into multiple steps. So this is called the antiderivative method. So and it works fine. This is going to be more intuitive to you. And it's totally fine if you want to use this method on the test. Again, this is preferred, though, because it generalizes more easily, and it also demonstrates some concepts really nicely. That the future position is the initial position plus the change in position. The change in position is a function. So there's a lot more concept built into this method. This method is more sort of plug and chug. Here we would have minus cosine of t plus constant of integration. So here we have the position function partially figured out, but we have to figure out what that c value is. And so to find that c value, we're going to come up and use this to solve for c. So whenever we do an indefinite integral, we end up with an infinite collection of antiderivatives. Right? Each c value gives you another particular antiderivative. So there's a whole family of antiderivatives. The indefinite integral gives you an unlimited number of functions. But if you have some initial value, that can pick off the one antiderivative that you're looking for. So we just plug those in. So we say S of 0 is 1. So if you plug in 1 for t, plug in 0 for t, you get 1 for S of t. So S of 0 is 1. So if we plug in a 0 over here, we end up with that. Once again, cosine of 0, go to 0 radians. Cosine's first coordinate, cosine of 0 is 1. So we end up with negative 1 on the right. Add it to the left, we get c equals 2. But then we have to go back in and substitute it for the c. And of course, we end up with the same answer. So both those techniques will work. It doesn't matter which one you use. I'll use the one on the left because it's a little more. You never are going backwards. You're always just moving forward. Here you've got a little jumping around to do. But.
May I ask a question?
Mm-hmm.
So in your FTC method, on your second line where it's 1,
Mm-hmm.
did you get the 1 placement there because you knew S of 0 was equal to 1?
Correct.
So that would always be like our initial start.
Exactly. So that's where that is the location on the number line where we start.
So we're only just skipping needing to solve for C between the two methods?
Yeah.
Okay.
Mm-hmm. That's right. Yeah, because this is a definite integral, there's no constant of integration. So you don't do that plus c thing. It's only when you have an indefinite integral that you end up with the plus c. So with that method, we don't have to deal with the c at all.
How were you able to do the 2 equals c to get to the same answer as the fundamental theorems of calculus?
This one?
Yeah.
So this is equal to 1, and then we add it to the left side and get 2,
Right.
and then we plug it back in right there.
Oh, okay.
You see, we come back to that and substitute it in.
Got it, because c equals c. Just like that.
Make sense?
And
Question?
And the fundamental theorem of calculus only works because it's S of 0? If it was
No.
S of
So if it was, so fundamental theorem of calculus is simply this step right here. If this was S of 4, if our starting position is at 4, then this integral would have to go from 4 to t instead of 0 to t. So the initial position locates us on the number line, and we're trying to look into the future. And so we want to integrate from whatever that starting position is into the future, so from whatever that number is to t, where t is a random number in the future. So if we had the initial position at, say, 3, then this would be 3 to t. Make sense? Yeah. All right, so here's one. You all start this one. I'm going to go fill my water bottle up. So same idea. Maybe I'll lower it down into the middle. So use whichever method, preferably the method on the left. How's it coming? Having fun yet? That winter break was so long. It felt longer than I never felt so disconnected. I think it's the longest winter break I've ever experienced here. It was like so long, which is good and bad. I got to go see some whales and swim with a manta ray. That was kind of fun.
Where'd you head to?
That was down in Puerto Vallarta. Super fun. Excuse me. It's so dry in here. So the instinct here, of course, is to notice that that's not just t. So you could use substitution. Is that a linear angle?
Yes.
Yes, the power on the independent variable there is 1, so it's linear. So we can use the RCR method just fine. So future position, super important, right? That's how we make money, if we can predict the future. If you can predict the future, that's how all these companies make money. So we're always using integration. If you're going to be an engineer or whatever out in the real world, the whole main point is to be looking into the future. You go collect data. You've got this data. You build a function, and then you integrate it to see what's going to happen in the future. That's kind of the basic gist. So we want to know where we are. That's the starting position. That's where we're starting from. And then we're going to add the change in position on the time interval from 0 to 4. Now, this is interesting. So they're giving us this time interval from 0 to 4. We're going to first find S of t in general, though. So we're going to plug in. We're going to integrate from 0 to t. And then for a dummy variable, we're going to do this. We're going to use an x, or whatever your favorite letter is. So that's how we're going to find. It's interesting that they didn't just say t greater than 0, because they're asking us for the position function. They're not saying what is the position. They're saying what is the position function, S of t. Right. But they've kind of restricted it to say, okay, well, we're only going to look at S of t from 0 to 4. It still means we use a t, though, because t can be moving from 0 to 4. They're sort of capping it off and saying this future position is only going to be accurate perhaps up until 4. So this t up here, we're imagining somewhere between 0 and 4. Okay, the initial position is 1. Time value of 0 is where we started, so now we want the change in position on this time interval from 0 to t. All right, so now our antiderivative outside function, you could pull the 3 all the way out in front if you want. It's just multiplicative. It doesn't matter. You can leave it on the inside. So the integral of sine is minus cosine. So that part comes out to the front. So we're going to have minus 3 cosine of pi times x. So we've anti-differentiated, i.e. integrated, the outer function. So that's what we've done so far. We integrated the outer function. And now we come in here and we say, oh gosh, that's linear. We're integrating, not differentiating. Take its derivative, and we divide instead of multiply. So the derivative of the inside is pi, and because we're integrating, we're going to end up dividing by pi. This is from 0 to t. So we're going to end up with 1 minus, usually we'll write our trig coefficients as, like that. Doesn't matter, of course. Those are equivalent. So there's our coefficient. Now we have to be a little careful. We're plugging in the t and the 0 to this, right? That part is our antiderivative. Like the 1 is just separate out there. So this piece right here. And then we can actually do two things there if we want also. There's a lot of ways. We can think of the negative 3 over pi as a multiplicative constant like that, and then do the substitution just into the cosine part. So you do cosine of the upper minus cosine of the lower and have this minus 3 over pi out in front. Does that make sense? So minus 3 over pi as a multiplicative constant, so we're sort of factoring it to the front before we do the upper minus lower part. So now we'll do the upper minus lower part. Plug in the upper, and we get cosine of pi times t minus cosine of 0 again. So cosine of 0, and cosine of 0 is 1. So we're going to have 1 minus 3 over pi cosine of pi times t minus 1. And we can leave it like that. That would be fine. We could distribute this minus 3 over pi now and say, oh, there's two constants. Let's group them together. Doesn't really matter. Because the constants aren't easily combined, it doesn't matter that they're kind of in two different places. Somehow we could combine them. We often would. So if you were to distribute this, there's not a whole lot of benefit to be gained. If they wanted, for some reason, to have the constant all grouped together like that, my math lab won't care. I don't care. If somehow those were easily combinable, it might be preferred to have it this way. And if you wanted to, sometimes with this simplification stuff, you can just go on forever. So if things don't easily combine, it's totally fine to leave it up here in this form. So that's correct. Down here, this is correct. Doesn't matter. Both of those are equally good. That doesn't look any better than that. Usually a lot of simplification steps are done in order to make things look cleaned up. But in this case, there's not a lot you can do. All right. Any questions on the concepts, the steps? Dusting off the integration skills. And this Calc 2 is all about becoming an integration ninja. That's your goal. Integration ninja. Give me an integral. The hardest thing about integration is that there are many functions you can't integrate. that look like you should be able to integrate. No matter how complex a function I give you to differentiate, you have all the skills to do it now. All those things you learned in Calc 1, I can write the nastiest looking function on the board, and you, it might be hard, but you have the skills to differentiate it, and it will have a derivative. I can write a simple function here, and you can't do it. That is not integrable with standard integration techniques. That's a simple function. E to the t you can integrate, but e to the t squared does not have an antiderivative in the sense that we've all learned about antiderivatives. There is no function that you know that will have a derivative equal to e to the t squared. So that's what makes integration hard, is that it takes serious detective work. It's like, you don't know, okay, am I just not finding the antiderivative? That's what's hard. Derivatives you can do no matter how complicated it is. You can use the chain rule, the product rule, the quotient rule, the power rule, blah, blah, blah. Integrals are harder because it's like division is harder than multiplication. If I give you two numbers, you can multiply them easily. I give you two numbers, dividing is a lot harder. Same thing with integration. It's just much harder than differentiation. And there are functions that you just can't integrate. So you've got to, that's why it takes so much practice. You've got to start figuring out, oh, can I do this? Can I not do that? Why? Question?
Yeah, so when you scroll up to where you got the 1 plus minus 3 cosine of pi x divided by pi, and when you got it to the right side, just when you factor out the 1 plus negative 3 divided by pi, right?
So the 1 is out in front.
Right.
And so then this negative 3 over pi, we're just factoring that to the front.
Oh, okay.
So that's being factored. This is multiplied by that cosine expression.
Right.
So that's just being plopped in the front, and then it's multiplied by the cosine expression. The cosine expression evaluated here gives two terms.
Okay.
So we have to have the parentheses. And you don't have to factor it to the front. It's just that a lot of times it's easier if there's a multiplicative constant to get it out of the way before you substitute. It often is a little easier, but not necessary. All right, let's go to, what did I just do? Can I undo what I just did? Control Z. It's a beautiful thing. Okay, so we're going to do the same type of thing in going from velocity to acceleration. So we started with position and we jumped over to velocity with this integration technique. Now if we integrate velocity, we'll get to acceleration. That make sense? All right, I said that backwards.
Yeah, I was gonna say.
I said that backwards. We integrated, what did we do already? We found position. Oh yeah, we started with velocity. So we found position from velocity. Yeah, but now we have to talk about how to get to velocity. And we get to velocity from acceleration. So now we're gonna, so we built position from velocity. Now we're gonna build velocity from acceleration. Yeah, I got tangled up in the, it only takes 3 things and you can get tangled up fast. So we already figured out how to find position from velocity. Now we're gonna figure out how to get to velocity from acceleration. Okay, so same concept. The future velocity will be whatever the initial velocity is plus the change in velocity on the time interval. Time interval is 0 to t. We're finding initial velocity at t equals 0. A lot of times we're just saying, okay, we're going to consider t equals 0 to be the starting point. If that was not v of 0, then this would not be a 0 there. So these two numbers have to match. Okay. So this is just generalizing the ideas. With position, velocity, and acceleration, we have names for s prime. S prime is v. And we have a name for v prime, a, acceleration. In general, you don't have names for things. And so if this was s prime, we could replace it with a v. If it was a v prime, we could replace it with an a. If it's a q prime, we just leave it as q prime. So with that sequence of position, velocity, and acceleration, we have names for those specific derivatives. In general, you don't, so you just leave it as q prime. So the net change in q If these were S's, that would be the net change in S, which is also called displacement. If it's V's, we could change that V prime to A, and over here we would just call that the net change in V. So here is just the generalization of how you predict the future from some random variable, Q, whatever it happens to be. So let's try. Starting with an acceleration, we're going to build up to velocity, and from velocity we'll build up to position. Using FTC, fundamental theorem of calculus. So the velocity in the future will be the present velocity, the initial velocity, the velocity at time 0, plus any net change in velocity. And the net change in velocity from our initial time value, 0, to future time value, which is represented by just the t. That's some t in the future. Now we want to integrate v prime, which has a name, a. And we need a variable for the integration. We've already used t, so we can't use t, so we just pick our favorite letter. We'll just use x. So that is our setup for the fundamental theorem of calculus method. Initial velocity plus the net change in velocity. So v of 0 is 50. And then this becomes minus 32 as a constant comes to the front. We're integrating with respect to x. So the integral of dx is x. The integral of dx is x. So we're going to have that. So then we have 50 minus, bless you, 32x. And when we substitute, so we're substituting right into this thing. That's our antiderivative. Plug in t, we get negative 32t. If we plug in 0, we get 0. So there we are done. So this is our velocity function of t. It's the velocity at some t value in the future, some t value beyond 0. And then we do it again. So now we have velocity and we want to get position. So position will be whatever the initial position is, plus any net change in position. Well, net change in position is just called displacement. And displacement on this time interval 0 to t, we integrate t's derivative, which is v. So we get, and then we have to just be a little careful. T is already in use, so we can't use a t. We can use whatever our favorite integration letter is. And that will give us position. Okay, antiderivatives. Antiderivative of 50, we're going to go with 50x. Negative 32x, add 1 to the exponent, get x squared, then divide by that new exponent. Negative 32 divided by 2 is negative 16. And that goes from 0 to t. Once again, that 0 is not going to contribute anything. Sometimes I'll just put a little mark there or something just so that, to indicate, oh yeah, this is giving nothing, right? When you plug it in, you get 0. Instead of always writing minus 0, sometimes we'll just not bother to write the minus 0 because it's unnecessary. So there is the position function. Okay, you all start this one. You've got an acceleration function, integrate it to get a velocity function, and then integrate again to get to position. See if you can get to position, preferably with the fundamental theorem of calculus technique. Oh my gosh. A rose. Pop your hand up if you have a question, if you're stuck on a step here, and I will nudge you in the right direction. Perfect. So everyone's seen how to use that reverse chain rule for this integration here? Integral of an exponential is itself. That exponent is negative x, which is linear. The derivative of negative x is negative 1, so we have to divide by negative 1. So we end up with a minus in front. And let's see, how many of you did this next step right? Do we have agreement? Any discrepancies?
I was a little worried about that.
Right? So let's make sure everyone's on board here. So here's our antiderivative. And I think plugging in the t is obvious, right? And then we subtract off. So we'll have a negative and a negative, which makes a positive. The antiderivative evaluated at 0, e to the 0 is 1. So we end up with minus 1, which gives us a plus 1. All right, and now we want to get to the position from velocity. So the position is the initial position plus the change in position, aka displacement, aka the function right there. Oops, can't use a t, already used t, so I'm going to move the dummy variable from t to x. Starting position is 40. And then we integrate here. The integral of 61 is 61x. All right, now we have that same type of antiderivative again, where we're going to use reverse chain rule. This exponent is linear, so we have to divide by negative 1, so we're going to get plus e to the minus x from 0 to t. So then we're going to plug in the t, and then subtract off antiderivative at 0. So antiderivative is right there. Plugging in t is obvious. And then we subtract off that same antiderivative evaluated at 0. Plug in 0 here, we get 0. Plug in 0 here, we get 1. We're subtracting off 0 plus 1, so we're subtracting off 1. So that's going to give us a 39 plus 61t plus e to the minus t. Whoops. All right, any questions on that? So we'll do one, I think we can squeeze in one last question, one last problem here. So this last one, this application, we're just doing, instead of using the S, the B, and the A, we're just going to do it with a regular population. So we've got this population of foxes. You're going out in the world and you can measure, right? This is empirical data. You can go out and measure how fast the population is changing. You can measure the rate of change. So that's the rate of change. We want to predict the number of foxes in the future, so we want to find P of t. So all we do to find P of t will be the initial population plus the net change in the population. And the net change in the population is just the integral of the population's derivative. We don't have another name for that in this case. We can't turn this, into a v or an a. We just leave it as p prime. Well, p prime is a function that's given to us. And they tell us that we're starting with a population of foxes 35. So 35 is given to us. This is going to be 35 plus the integral from 0 to t of this derivative function, 5 plus 10 sine. I'm going to be suggestive here and write this linear function like that. And I can't use a t, though. Must use an x. So I'm going to put an x. So I'm going to put an x in here, put parentheses just to distinguish it as the angle. So we have that. All right, so pi x over 5, that's a linear function. You can think of it as pi over pi fifths, pi over 5 times x, or pi x over 5, same thing. When you're differentiating, it's easier if that coefficient is sort of positioned out in front. Okay, so then we do our little integration process here. We're going to get 5 times x plus 10. Okay, integral of sine is positive or negative cosine?
Negative cosine.
Negative cosine. So I'm going to write it like this. And again, I'm just going to leave this kind of like that. Now, this is linear. So we divide by the coefficient. We take the derivative of the angle, which gives us the coefficient, divide by that, and then we get evaluation from 0 to t. Plugging in the t is pretty straightforward. That's going to be 35 plus 5 times t minus, okay, this division, dividing by a fraction means multiply by the reciprocal. So negative 50 divided by pi. And then this is going to be cosine of pi over 5 times t. That's in our angle place. And now we have to subtract off antiderivative at 0. So let's just make sure we're thinking smoothly here. There's our antiderivative. If you plug in 0, that's gone. What's cosine of 0? 1. So that's all 1. And we're subtracting this off. So if we're subtracting this off, minus times minus is positive. So we're going to get positive. If that's just a 1, we end up with 50 over pi. Everyone agree that that should be positive 50 over pi? So when we plug in the t, we get this thing right here. When we plug in 0, that goes to 0. That goes to 1. We're subtracting off that whole thing evaluated at 0. So minus a minus is positive. Pi divided by 5 flips and gives us 50 over pi. That is our answer. So we don't have any way to combine these constants, so we can just leave it like that. And just tell me, with words, If we want to know the population in 15 years, what do you think we do?
0 to 15.
So if we were studying from scratch, we would integrate 0 to 15, but if we want
15.
P in 15 years, all we do is plug in 15. If we want the population in 35 years, we'll plug in the 35. All right, so let's stop doing math. And every day after class, I'll stay here. And, my office hours are right after class for an hour. I'll stay here as long as you need me, and then I'll just go to my office. So if you want more help, you can come down there. If you just want to stay here and do math, you can do math. Welcome, 2025, spring. Shocking. Shocking. Get your OneNote thing going. Check that email. And again, if you don't see it in your email, do a little search for SharePoint. It should be there. And then make sure that when it opens in the browser, click the Open in App. And let me know if you have any questions on it. Let me hit stop on this recording, and then we will start.